Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to apply work-energy methods to kind of a combined problem or a system that's kind of tied together. In this example, we're going to include a frictional coefficient of 0.2 and see how that affects the problem. So, in order to apply work-energy methods, the first thing we do is label the position of our particle or our system. So I'm going to call this position 1. While I'm at it, I'm noticing there's two different particles, so I'm going to call this particle A or mass A, and I'm going to call this one mass B. Here's position 1, where the 20 kilogram mass is 2 meters off of the ground here. The position 1 is going to be right here in, as far as mass B is concerned. Now I'm going to imagine mass A accelerating down. Here's kind of a snapshot of it right before it hits the ground. I'm going to call that position 2. There's a velocity down equal to v2. Mass B is accelerating left, presumably. We'll triple check that here in a minute. Here's position 2 for mass B. It's moving to the left with some speed. I would call it v2. Now, before we even move on, we should just make sure the system's even going to accelerate. Right? Conceivably, there's enough friction to hold mass B in place. So before I move on, I'm just going to kind of look at the system here. If it were static, the two forces acting on this mass would be equal. We would have a tension up, its weight down, mg, and I'm just going to do this without a calculator here. That tension would be approximately 200 newtons. Right? Mass is 20, g is about 10. If I take a look at this mass, we have a potential or a force to the left, a tension. If this is static, that would be 200 newtons. We've got a weight down, 300 newtons, a normal up. Now, by Newton's second law, for sure this thing's not going to accelerate up. So the net force on this free body is up. The normal would be 300 newtons. The frictional force would be, in this example, we're looking at around 60 newtons, 0.2 times the normal. And 60 newtons is quite a bit less than the tension here, the 200 newtons. So this thing is for sure going to accelerate. Now, I had intended on this frictional force being a sliding frictional coefficient. You know, even a static frictional coefficient of double that, 0.4, is going to give us a frictional force that is not enough to overcome that 200 newtons. So this thing is in fact going to start accelerating, but I just wanted to take a little time here and demonstrate how I know that. Alright, I'm going to get rid of some of these force vectors and things I don't need. Oops. Can't get rid of that without erasing it apparently now. So I don't need this force vector. I'm going to go ahead and get rid of it. Don't really need this one either. Alright. So now we know definitively this system is going to accelerate. I've defined my system at state 1 and at state 2. And now we're going to go ahead and write out the work-energy theorem. Right? PE1 plus KE1 plus work equals PE2 plus KE2. I'm going to go ahead and define a datum. This would be a nice logical place to put a datum. So we're going to measure our potential energy with respect to that line. Now, with this datum, the mass A has a potential energy of mgh, where that mass would be, again, mass A, the 20 kilograms, the h would be the 2 meters. Mass B has a potential energy with respect to this datum, but if you've watched my previous video, one thing I pointed out was this height and this height are the same height. So whatever I put for PE1, an mgh term, it's going to be the same under the PE2 term. It's just going to subtract off anyway. So long story short, when something is not changing in potential energy, you don't need to worry about its potential energy. So that term, the PE1 term, done. The KE1 term is 0 if the system starts from rest. I'm going to hold off on the work term and do that last. The PE2 term. So mass A is now at our datum, so its potential energy is 0. Mass B, we're not considering its potential energy because it's not changing. It's important to note here, though, that how I define my system, I'm including the mass B, mass A, and the rope between them. So the kinetic energy, when I calculate it, I need to include both in my system. So we're going to have a 1/2 mass A V, go ahead and just put V2 squared, but I need to include a kinetic energy term for the second mass, 1/2 mass B times V2 squared. Now, honestly, if the rope had a significant mass, I would need to include a kinetic energy for the rope too, but I'm going to assume the rope has a small kinetic energy compared to the rest of the system. Now, work terms, and I talked about this in my previous video, but I'm going to go ahead and go through all potential forces we need to worry about. We have a gravitational force acting on this mass, mg. That force does do work, but that's taken into account here. There is a tension acting on this mass. We don't need to include that because it's, in a sense, an internal force to the system, at least as far as work energy equations are concerned. If I do try to include a work term, it's going to be minus T times H. However, if I come over here, there's another tension, and it's the same tension. The work term for this force is going to be positive T times H, and when we add these together, we're going to get 0. So we don't need to include a work term for the tension as long as we consider both masses as our system. One could argue that there's a force applied here to the string or the pulley, if you want to include the pulley in the system, but there's no displacement for that force. This point isn't moving, so there's no distance to multiply by, so we got no problems there. Alright, force is acting on mass B. We have a tension acting to the left, but we already talked about why we're not including that. We've got a gravitational force down, mg. Surface in contact would give us a normal up. And if we include friction, we'd have a frictional force along this surface, which is going to be to the right. Now, as far as which of these forces are doing work, we don't need to consider the tension. Well, we already have considered the tension, but because that tension is an internal force, and I'm including both masses, we don't need to worry about it. Again, even if I try to include a work term, they're going to add to 0. The normal makes a right angle, so there's no work term for that. The mg makes a right angle, so again, no work term for that. But there is this frictional force here, and that one is doing work. It is parallel to motion. The work done by that force is going to be minus the frictional force times the distance it moves, which in this problem is 2 meters. It's the distance called h, so I'm going to go ahead and put minus f times h. Now I'm going to clean this up before I bring it over here and insert it into my work energy equation. The frictional force can be written normal times coefficient of friction. And looking at our free body here, if I wrote out this equation, sum of all forces in the y direction equals 0, I guess I'll go ahead and just do that. Sum of all forces y direction equals 0 for this free body. We're going to get plus n minus mg equals 0. So the normal is equal to mg in this problem. mg. So the work term can be written minus mg times the coefficient of friction times h. Now the m, let's be clear, it's mass b. So I need to tack a little b on there. So the work term acting on mass b can be written minus mass b g times the coefficient of friction times h. I'm going to go ahead and put all that in there. Minus mass b times g times the coefficient of friction times h. And there's my completed work energy equation, taking into account the fact that we have an external force here, an external frictional force doing work on the system. I'm going to go ahead and put numbers into this thing now, and I'm going to put NCU here, which stands for note consistent units. So this is going to read 20 times 9.8 times 2 minus 30 times 9.8 times 0.2 times 2 equals, all right, very similar to the previous problem, mass A over 2, or 1/2 mass A, would be 10 V2 squared plus 1/2 of mass B, with mass B being 30, would be 15 V2 squared. I'm going to go ahead and just get a number for that now. Give me a moment. And on the left-hand side of that, I get 274.4 equals, and these things add to 25V squared, that's V2. So V2 is approximately 3.3 meter per second. I think in the previous video when I worked this without friction I got 4 meter per second, so that's making some sort of sense. Alright, I'm going to go ahead now and do the motion study just like I did before. I'm going to study the motion of this system, putting a coordinate system here, a plus x with down positive. I'm going to go ahead and draw a velocity graph for mass 2. Again, the velocity graph describes what the velocity of that particle is doing. Right? So velocity against time. From experience, hopefully you've seen enough of my videos and worked enough of these yourself, you would know that if you find the acceleration of the system, you're going to get a constant value, which means that our velocity is a linear function. Right? We don't know when it's going to hit the ground yet. We'll just call that time t. But we do know the final velocity is 3.3 meter per second. We also know it's going to travel a distance of 2 meters. In terms of this coordinate here, this plus x I put, that's a delta x is 2 meters. And that's equal to this area bound in this curve here. So that's going to be 1/2 t times 3.3 meter per second. And we can solve that for t. And I get 1.2 seconds out of that. 1.21, I'm going to go ahead and just round that to 1.2 seconds and say approximately. And then our acceleration, which is rise over run. Now keep in mind on the graph, that's the rise, that's the run. So the acceleration is going to be 3.3 meter per second over 1.2 seconds, or in other words, approximately approximately 2.75. I'm just going to say about 2.7 meter per second squared. Normally 2.75 you would round up. I would argue that, well, I rounded to 2 sig figs kind of all over the place anyway, so I'm just going to leave that 2.7. Maybe it should be 2.8. Let's see, 2.75. I'll go ahead and round that to 8. So that I'm following the rules. At the 0.5 we round up, but again, not an important part of this problem. Important points of this problem: how to write a work energy equation. Always label your two positions. So we got position 1 and position 2. Write out your work energy theorem for it. It's very important to realize in this problem that you're going to want to define your system as both masses together. So this is the system I'm writing that equation for. Because if you don't, if you write the equation for just one of these masses, you have that tension, which is an external force doing work. You would have to include that. And then, how would you solve it? Well, you'd come over here and write another work energy equation for that guy, and you'd have an external tension doing work, and you'd put those equations together. It will work out fine. You can do that. But it's important to note that as long as you define your system like this, you don't need to worry about the tension. It's internal force. Even if you try to include work terms for it, they're going to add to 0. But as a consequence of that, you have two kinetic energy terms. So I hope this video helped demonstrate these concepts. Have a great day.